already mentioned in the previous video. Now we are going to discuss about the numbers which are not rational. So, a question. Are there any numbers which are not rational? And how can we define them? Yes, there are many numbers which are not rational. And we can also define them. They are just the opposite of rational numbers. So, what is the definition of rational number? They are numbers which can be represented in the form of p by q, where p and q are integers and q not equal to 0. So, irrational numbers can be defined as the numbers which cannot be represented in the form of p by q, where p and q are integers and q not equal to 0. So, these irrational numbers and rational numbers together make the real number system, denoted with the letter R. So, now we are going to learn about how to represent an irrational number like root 2, root 3 or root 5 on a number line. First, we will draw a number line and mark them 0, 1, 2. Now, we will draw a perpendicular at 1. This is 1 centimeter, and the distance between 0 to 1, let it be 1 centimeter. Now, if we join this becomes a right angle triangle. Now, if we want to find the measure of this hypotenuse, we will use the Pythagoras theorem. So, root of 1 square plus 1 square is equal to root 2. So, this is root 2. Now, we will take a compass and measure this distance and draw an arc like this, which is something like this, and this is the point where root 2 lies, and the approximate value is root 2 is 1.414. Now, if we want to find root 3, again, this is the length of root 2. Now, we will again extend this 1 centimeter perpendicularly and join to the 0. Now, this again becomes the hypotenuse, and we can find the value by root of root 2 square plus 1 square, which is nothing but root 3. So, this is root 3. Now, if you measure this distance and draw a arc like this, it will cut here, root 3, which is approximately 1.732. Now, we have learned how to represent irrational numbers on a number line, and we have learned that both rational numbers and irrational numbers make up the real number line. Now, we are going to solve the exercise 1.2 of this chapter. Okay, we will solve now the exercise 1.2 of the chapter number system. So, the first question of this exercise is true or false. So, the first question is, every irrational number is a real number. Yes, every irrational number is a real number. And the second one is, every point on the number line is in the form of root of m. See, This one's false because take some examples like 2, 3. These can't be expressed in a form of root m. Okay? Now, the third one is every real number is an irrational number. That is also false. Real numbers consist of real numbers and irrational numbers and irrational numbers. So this one's false. The second one is are the square roots of all positive integers irrational? If not, give an example of square root of a number that is a rational number. The question is the square root of every rational number is irrational? All positive numbers, rational numbers is irrational. If not, we should give an example for proving. Yes, we can give. No. The answer is no. Because root of 4 equal to 2, which is rational, and root of 9 equal to 3 rational. I guess there are infinitely many rational numbers which are roots of other numbers. Okay. Now, the fourth question of this exercise is represent root 5 on a number line. And I have already told how to do. If you want to represent any irrational number, root n on a number line, first you should draw the number line and mark the distance of root of n minus 1 and that is of 1 centimeter perpendicular B. So again, we use the Pythagoras theorem to find the length of this hypotenuse, which is nothing but root n. Then you should draw an arc cutting like this to show that root n lies here. Similarly, we will use this technique for representing root 5. First, we will draw a number line and mark its point. So, root of 5 minus 1 to the root of 4, which is 2. So, we will get 2 centimeters here and draw 1 centimeter perpendicular and join the vertices, and this is the hypotenuse. So again we use the Pythagoras theorem to find the value of this. So 1 square is 2 square whole root, which is nothing but whole root of 1 plus 4 is root 5. So this is root 5. Now we will draw this like this, and this is where root 5 lies. Okay, and the sixth one is a classroom activity which you can do yourself. Okay, now we are going to discuss about decimal expansions of rational numbers. So, what do we mean by the term decimal expansion. Decimal expansion is nothing but the representation of rational number in its decimal form. Now we will observe the unit fractions in denominators from 1 to 10. For example, see 1 by 1. Its decimal expansion is 1.0. 1 by 2, it's 0.5. Now 1 by 3, it's 0.333 and so on. It's never ending. And 1 by 4 is nothing but 0.25 and 1 by 5 is nothing but 0.2 and 1 by 6 is nothing but 0.1 6 6 6 and so on. 6 gets repeated itself. 1 by 7 is nothing but 0.1428, something like that. And 1 by 8 is nothing but 0.125. And 1 by 9 is nothing but 0.1 bar, which means 0.1111 and so on. And at last 1 by 10, which is 0.1. So what do we observe from this? See, from this we can define rational numbers from a different way, perspective to be exact. So, the decimal numbers which end are called terminating, and which do not terminate and repeat themselves are called non-terminating and recurring or repeating, anything we can say. So from this we can define rational numbers as the numbers which are said to be rational when the decimal expansion is either terminating or non-terminating and recurring. So, the irrational numbers are exactly opposite to this. It is non-terminating and non-recurring, which means the decimal expansion doesn't repeat itself. So, that is called an irrational number. Okay, now we will represent this on a number line by using the decimals. So, in order to express or represent decimal expansions on a number line, we use a method called successive magnification. So, what does successive magnification means? It means magnifying repeatedly. So, for example, we need to find the decimal number on a number line. For example, say 0.45. First, we draw the number line and mark 0, 1, 2. Now, 0.45 is between 0 and 1. So, we magnify this part. Again, we draw a number line with 0 here and 1 here. Between, there are 10 parts. We divide them into 10 parts. So, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and 1. Now 0.45 is between 0.4 and 0.5. So we again magnify this part and divide it into 10 parts. Here 0.4, 0.5, 0.41, 0.42, 0.43 and 0.44, 0.45, 0.46, 0.47, 0.48, 0.49 and 5. See, we can find 0.45 here, and this is the number we need. See, now as we learned that rational numbers can be expressed in the form of decimal expansion, right? So can we reverse this action, which means can we represent decimal expansion in the form of rational number? Yes, we can. We can represent decimal expansions in the form of rational numbers. Now we are going to discuss about that. How can we represent a decimal expansion in the form of a rational number? Well, it's an easy task. For example, take a decimal expansion 0.5. So how can we represent it? Simply we will make 5 by 10, which is nothing but 1 by 2. Now, what about 0.3333 and so on? We can't put the denominator with infinity zeros, right? So what we do is use a little algebra for this. For example, let some variable x be equal to 0.333 and so on. And 10x is equal to 10 multiplied by this gives 3.333 and so on. Now 10x is equal to 3.333 and x is equal to 0.333 and so on. We subtract them. Now this becomes 9x and this becomes 3. This all cancel out to be 0 and 9x is equal to 3 and x is equal to 3. X is equal to 3 by 9. X is equal to 1 by 3. We can even cross check whether this is the right answer or not. Well, this appears a little clumsy or difficult. So I will explain another example. For example, let us take 0.111 and so on. So x will be 0.111 and so on, and 10x will be 1.111. So if we subtract them again, the same answer, 10x minus x is 9 and this all cancel out to be 0 and 1. And x is equal to 1 by 9. It's very simple if you understand. And now Can irrational numbers can be represented like this by using this? No, they can't. Well, now I will discuss a very interesting decimal expansion, that is 0.9 bar. And that can be represented in the form of a rational number. That can be very interesting. Well, I will show you that. So, let us try to represent 0.999 and so on in the form of a rational number. Okay, now, same method. Let x is equal to 0.999 so on, and 10x is equal to 9.999. Now we do the subtraction. 10x minus x is equal to 9.999 and so on, minus 0.999 and so on. We cancel out to 0 point, and this is 9 and this is 9x. If we do the further calculation, x is equal to 9 by 9 and x is equal to 1. But one can be written as 1 by 1, but 1 by 1 is equal to 1. But 0.99, and this is where the trick comes in. 0.999 is almost equal to 1 at infinity. At infinity number of places, 0.999 is almost equal to 1. That is why we got the answer as 1. Now, let us see the value of pi, whether it's rational or irrational. For example, you will take a circle, the circumference C and diameter D. So the value of pi can be written as pi is equal to circumference divided by diameter. Well, pi is an irrational number, right? But here it is represented in the form of p by q. Well, is pi rational or irrational? Well, pi is an irrational number because, see, we take the value of pi as 22 by 7 for our convenience, but the exact value of pi is not till known. You should know for at least and the maximum number of infinity number of places for the exact value of pi, which is almost impossible. So, for our convenience, we use 22 by 7 as the value of pi, but it is a very approximate value of pi. It was first approximated by Archimedes. See, if we take a circle and measure it with a thread, it gives its approximate value. We can't measure the exact circumference of a circle. So, the value of pi cannot be exact until a C is known exactly. Understand? So, in this way, pi is irrational. So, now, in the next video, we will try to solve exercise 1.3 and 1.4. So, thank you.